Alright, so we've done a lot with limits. We've done limit as x approaches c of a bunch of different functions. We've done rational, we've done polynomial, we've done trig functions. Now the question is, what happens whenever we have the limit as x approaches infinity? So this is limits at infinity. So what do we mean by limits at infinity? Is now, instead of looking at x approaching a number, we're going to look at what happens when x approaches infinity of a function. That's what we mean by saying a limit at infinity. So instead of looking at x approaching a number, which is what we've done this whole time, what happens as x grows without bound, or what happens when x shrinks without bound? Now to say that the limit as x approaches either plus or minus infinity is equal to a number, that means that y equals L is a horizontal asymptote. So horizontal asymptote. So before we had a lot of people asking, how do you find asymptotes? Well, now we know. We know vertical asymptotes is wherever a limit is plus or minus infinity, and a horizontal asymptote is a limit at infinity. So we'll write that. So a vertical asymptotes are always of the form x equals c. This occurs if the limit as x approaches c on the left or the right, it doesn't matter. So I'll say plus or minus is equal to either plus or minus infinity. And now a horizontal asymptote these are of the form y equals some number L, and that's true if the limit as x approaches plus or minus infinity of my function is equal to L. What this is saying is that in the long run, so as x grows huge or it gets really small, my y values are approaching a number L. That's a horizontal asymptote. So again, vertical asymptotes are of the form x equals a number. So if you think about a graph, that would be a vertical number, or a vertical asymptote, x equals a number, if the limit as I approach that value is plus or minus infinity. So one of those two things on the left or right. A horizontal asymptote is of the form y equals L, and what this says is that it's equal to L if in the long run my function approaches L. So that's a vertical and horizontal asymptote. We know how to do that. So how do you evaluate these limits at infinity? Well, the ones that we're going to look at are generally polynomials or rational functions, or you could just look at the graph. Let's look at the limit as x approaches infinity of 1 over x. If we look at the graph of 1 over x, it has a vertical asymptote at 0, and this is my function. So I'm talking about what's happening as x grows larger and larger. What are my y values doing? Well, you see, as I grow larger and larger, my y values are approaching the x-axis, and that's where y is equal to 0. So I have that the limit as x approaches infinity of 1 over x is just 0. What about the limit as x approaches negative infinity of 1 over x squared? Again, let's look at my graph. 1 over x squared has a vertical asymptote at 0, and this is what my function looks like. As x goes towards negative infinity, so now I'm saying along my x-axis, my x's are going all the way to the left, what are my y values doing? Well, again, they're approaching the x-axis. That's where y is equal to 0, so limit as x approaches negative infinity of 1 over x squared is again 0. So all I'm asking now is, as x gets huge, what are my y values doing? Here it was, as x gets really small, what are my y values doing? So that's what we mean by limits at infinity. Now here's a theorem that might help us. For n greater than 0, the limit as x approaches infinity of x to the minus n is equal to 0. And if n is a whole number, then the limit as x approaches negative infinity of x to the n is 0. Now if n is not a whole number, we can't necessarily say this, but For n greater than 0, the limit as x approaches infinity of x to the minus n is 0, and if n is a whole number, then the limit as x approaches negative infinity of x to the n is 0. One thing you might want to recall is that x to the minus n is 1 over x to the n. So that's why we're saying this. So let's do a couple examples of that. What's the limit as x approaches infinity of 1 over x to the third? Well, x to the third is really x to the negative 3. So here I have it x to a negative power where I'm approaching infinity, so this has to be 0. What about the same problem where x is approaching negative infinity? Well, again, I have this is x approaching negative infinity of x to the negative 3. Since this is a whole number, I know that as I go towards negative infinity, it goes towards 0. That's what my theorem just told me. Now, if it's not a fraction, we don't know exactly what to do with that yet, but for now, that's what we can say. So now we know how to evaluate a limit as x approaches negative n, where n is a whole number.